Yeah, so this is lecture number 1, analog circuit design E211. So this is 0. So it has one laboratory session, 2 lectures per week, and it's in total 3 credit. It's going to have 2 lectures. One is on Wednesday from 9 to 9:50, and Friday 10 to 10:50. So these 2 are the lectures in 8 and 1A. And on Monday we have laboratory from 11 to 1. So it depends. We'll try to complete in 2 hours. Right. So generally this course is compulsory for mostly every engineering college, electrical, electronics and communication or instrumentation. They study this course. Right? And there are lots of application or the industry where people use the knowledge of analog circuits. One is called integrated circuits, commonly known as IC. Some people also call it VLSI. You heard about VLSI? It's a very large scale integration. So this is one of the foundation course for VLSI. Other than that, if you are interested in power electronics, still this course is very important. Communication engineering, where you want to understand analog modulation or the modulation in general, those things require actually analog circuit design knowledge. And of course, the RF and micro engineering. So any of the course if you want to take, it's desirable that you should have analog circuit design course before having these courses. And this is very important for, in general we call this one as design course. So generally design has 2 branches, one is called analog and one is called digital. So if you are doing design, then it's having both the things. Okay. Before going to this, let's look at this. Okay. So as we have decided, we will have 4 assignments. Each one of them will have the weightage of 4 marks, and 5 surprise quizzes, right? And other than that, 2 exams, just midterm and exam, something like quiz 1, quiz 2. Okay. Okay. So this is about lectures, and about laboratory. We are going to follow one strict rule that we are going to write the LaTeX report. Right? It is expected, it is prerequisite to know the LaTeX. I am not supposed to teach the LaTeX. Okay. So in TCF somebody wrote that I had to teach LaTeX. I am not supposed to teach LaTeX. Okay. So, but now every one of you know how to write reports in LaTeX. So we have to get less than 15% plagiarism. We can send it to library and we can check whether it's less than 15% plagiarized or not. Each one of the experiment has weightage of 2 marks, so that's how it becomes 14%. At the end, at the like 1 day before your DP, we'll have one project. So it's a so you have to make some project which is electronics project. It might be part of DP. I don't care about it. Okay. So whatever you are doing in DP, that if you want to do it in this project, that's also okay. No problem. Right? But we'll allocate some extra money from here. It will not be like 30,000, maybe something like 4 or 5,000. I don't know, right? So that you can make the project. This project is expected that you are going to make some circuit. It has to be electronics, and you have to make PC boards, or people call it PCB. So printed circuit board, this requires actually money, and you have to solder it and then you have to run that. So generally all professionals use PCB, they don't use breadboards. So let's learn it here. in this course, right? So, and at the end you have to submit the project report. Has to be less than 15% plagiarized. It has weightage of 10%. Okay. And if everybody agrees that they are coming on time, if everybody agrees they are coming on time, I don't want to take attendance and all these meetings. Practice meeting, I don't like that. But if all of you are coming on time, okay, then it's okay. So this is the course content. So we are going to talk about. Unfortunately, it's only two credits of lecture, so I'll try to justify as much as possible. But it's going to have two things together: BJT or MOSFET amplifier design. So it might be single element and differential. For that, you have to look at the frequency response. And other than that, we are going to study four different topics known as output power amplifier, oscillators, PLM, ADC, and DAC. So this is, by the way, phase law 2, and this is analog to digital converter. And other side is digital to analog converter. So these are the topics which we are going to study in this course. And maybe using these many things, you can design something as a project, right? By the way, anybody know about what is oscillator and what is PLM? What is the use of oscillator and PLM? Any guess?
So oscillator is used to wave.
Okay, so you are saying like this?
Yes.
Yeah. So he's correct, but it can generate sine wave, something like oscillatory sine wave. So if you remember in school time, you must have studied the resonance. So using resonance, we are going to oscillate the output, which which will be used to design, create a square wave, which is going from logic 0 to logic 1. By the way, these values, like on top of this average value, there is some V1 and minus V1. This is not very big number. V1 V1 is in the range of something like 100 millivolt. But we want to have logic 0 to logic 1, means 0 volt to sometimes 5 volt, or sometimes some different, or sometimes minus 5 volt, right? Logic 0 and logic 1 are defined separately. It depends on your technology. So to make that, we have to make one negative feedback loop, which is going to give you the square wave, or it's going to act as clock to all the digital system. That's known as PLM. Like, although the world is analog, but we like to process everything in digital domain. So that's why, like, we are studying ADC and DAC. So ADC and DAC are actually kept everywhere, and if you know this, like, this is the this is the place where people are getting mostly all the jobs. ADC, DAC, PLM. These are the small things. Without without knowing these three topics, you cannot design PLM and ADC. Right? So the core strategy is as follows. Like, I'm going to start with the understanding of small and large signal. So there is something called small signal and large signal analysis, through which you can analyze any circuit, or you can understand any circuit. So there are many ways. Generally, people start with the device physics, but I believe physics has been taught in IC 161. So it's not part of this course. So there is no physics. Right? There is no physics in this course. So diode and all other things are not there. You study diode in IC161, right? The diode BJT. You also have made common emitter amplifier, but we are going to make common emitter amplifier one more time in the laboratory just to understand how it works. And like in the starting, we are going to make one rectifier also, just to clarify some of the things, so that you can understand what is single-ended and differential probes. So without that, I'll just give you one. If you remember the bridge rectifier, right? So bridge rectifier. So we are expecting that the output will look like this one, right? Full wave rectifier. So we have to see this voltage versus time. Is there anybody who has seen this output in BTech first year? You have seen it, Saket? Okay, let's see, because as per my knowledge, it's difficult. You have to do something, then you'll get this. Generally, people get this output or this output. So this one is like there is a trick so that you can see in IIT Mandi's laboratory. Right? So we will start with this experiment. Anyway, so to analyze that, we are going to use small and large signal analysis, and we are going to find out the input and output impedance. I believe every one of you know the Norton and Thevenin theorem. So we are going to use that to find out input and output impedances. Then understanding of parasitics. So parasitics, generally parasitics are inductor, capacitor and resistance also. But when we are adding inductor and capacitor, it changes the order of the system. So that will give you the frequency response. Or through the parasitic understanding, you are going to write down the transfer function of the circuit. And then using this, we are going to make the design of amplifier. So whatever is inside operational amplifier, we are going to study that. Inside operational amplifier, not the triangle. This triangle, it is expected you know about this triangle, how it works and all. So we are inside this triangle. And once this is done, like we are going to study the system level understanding, like oscillator, generally known as voltage control oscillator, then phase lock loop, ADC, and that. So, and same thing we are trying to understand this, the experiments. So it will be going hand by hand, right? So there are 14 weeks are there, and there are 7 experiments. And one of the experiments will take only one turn. Other experiments will take 2 turns, and you have to submit your report within 7 days. So when you are coming next time, it has to be submitted in a group of 3 or 4, whatever, 4, right? And same marks will go to all 4. So please do not complain that other guy has not worked or whatever. Okay, I am not looking into this micro level. Is it okay, or you want me to check that? We can keep some viva. Okay. Okay. So throughout the course, I am going to follow. This is if you are in this particular time, this is the only person who is considered as Newton of this particular domain. It's Behzad Razavi. So he was a professor in Sharif University in Tehran earlier, and thereafter, right now he is in UC Berkeley. Right. Other than that, Behzad Razavi has written many books, almost like 11, 12 books are there. This book will be in red color with white color text. However, there is one more book called CMOS Analog IC Design by same author, by Behzad Razavi. But this book is blue color. This is blue color. Sometimes I am going to use this. Sometimes, right? But this is more easier book than this one. This is written for only and only for CMOS. There is nothing like BJT. So I'm going to try to touch BJT and MOS together. But majorly we are going to talk about MOS. Okay, so let's start with the course. Important terms are like large signal and small signal. As I told you, we have to understand what is large signal and small signal. We talked about this, right? Yes or no? Right? So maybe let's check whether you know or not. So this is an amplifier. This is 15 volt and minus 15 volt. If this gain is, let's assume that 100. If I am applying 5 volt output, 5 volt input, what is the output? 15. Okay, so 15 volt output because it's saturated, and 5 volt, is it small signal or large signal? So this is known as large signal. We have to make sure that it should not touch plus 15 and minus 15 or the plus V supply and minus V supply. Plus V supply and minus V supply are generally known as rail. If you find word called rail, it's referring to power supply, either plus V supply or minus V supply. So these are the things like what is large signal and small signal. We know that rail to rail value, when we are saying rail to rail, it means plus V supply to minus V supply is the value from positive V supply to the negative supply value, right? And of course we know that output cannot go beyond plus V supply and minus V supply. So this is what we have to remember. Okay. So I believe you have seen this one, right? This is called MOSFET. It's called metal oxide semiconductor field effect transistor. I can write down for you. Metal oxide semiconductor field effect transistor. So this is the one which works with field, means voltage. It does not work with current. Like the case in BJT, where if you have remember, it works with the base current IB, right? So like IC equal to IE plus IB and other equations we used to follow. So in this case, it's not current control device, but it's a voltage control device, and it's VCCS. You remember what is VCCS and which particular device is categorized as voltage control current source? Like what is the characteristic of this one? So you have to see what is the input and output impedances, right? So if input impedance is infinity, output impedance is infinity, we are going to consider that particular device as voltage controlled voltage source. So there is one table which is very popular one. So there are 4 different possibilities: voltage controlled voltage source, voltage controlled current source, current controlled voltage source, current controlled current source. So there are impedances which has to be seen, input and output impedance. So in the case of voltage controlled voltage source, input impedance is infinity, output impedance is 0. In the case of VCCS, input is infinity, output is infinity. In this case, it's the reverse of, right? So this is the standard table where, but note that, let's agree on one more thing. VC, CCVS. So input is 0, output is infinity. No? Hmm? Yeah. Sorry, I made a mistake. It's voltage. It cannot rise. 0, 0. This is 0, and this is infinity. Right? Okay. So we have to follow this table. There are many other ways to debate on this particular devices, VCCS, VCVS, or other devices. So on the basis of physics, people can do that. But in my opinion, like this is the best way, right? To know that whether we have to apply voltage or current, because sometimes you don't know that whether I should apply input as current or voltage. If you apply some other quantity, it cannot drive, or you have to make one more stage called voltage to current converter or current to voltage in between, or some buffer, so that it can drive, right? So field effect transistor is the one which has characteristic of VCCS. So have you seen how MOSFET look like, cross sectional area? Have you seen? Okay. So if you have not seen it, it looks like this one. So it looks like this one, where there are four terminals, not three. Unlike BJT, it has four terminals. One is called gate, one is called drain, one is called source, and one is called body, oblique substrate, or bulb. If you are hearing any of the words, all are synonyms to each other. In different era, different people have given different names. So if you are following Reza Ghazali, he is going to call substrate. If you are following other books, they are following bulb or body. But all new engineers, if you go to the company, you find that people are calling it body. But all are synonymous. Any one of the word you can follow. So if you look at this structure, here generally we are keeping some metal contacts. This one is metal contact. This one is silicon dioxide, and this is P-type substrate. You know about N plus P, all this, right? In school, you must have studied P substrate, P semiconductor, N semiconductor, N plus, all this. However, we are going to repeat that one more time, but right now to understand this figure, I assume that you understand N plus P and all. So if you're looking from top, so there are three things can be seen. So this is metal. Silicon dioxide is commonly known as type of oxide, and this is P-type semiconductor. So in total, it's known as MOS, metal oxide semiconductor, and as it is operated on the basis of voltage, it's known as field effect transistor. So in total, it's known as MOSFET. So this technology was introduced earlier than BJT. So this was not the older technology, but this was the this is not the newer technology, but it's the one of the oldest technology. However, people didn't know how to use this one. At that time, it was not mature enough, and like just MOS does not help you. But if there is something called CMOS, complementary metal oxide semiconductor technology, where not only NMOS but that technology has also availability of PMOS. So NMOS and PMOS are together. So as many number of MOS, NMOS you have, same number of PMOS are there, and this gives uh, a better swing and better possibility to use it for specifically for digital technology. Unfortunately, still analog is not so much mature enough, and that's why like analog is still difficult and it's not automated. For digital, you can write a code and you can generate all these circuits, but for analog, you have to design it. So that's the major problem, and that's why like analog circuit designers are paid more than digital. Or in industry, analog has more respect because very few people are there in the world who are in analog. Right? Okay. You must have studied something on FPGA in digital design, DSD, right? Digital system design. So you are writing code in Verilog or something, right? Verilog, VHDL. So then you can burn it in FPGA, and FPGA has actually the logic gates which are actually designed with CMOS. So NMOS and PMOS all are there. So that particular technology came up and solved all the problem of digital. Still, analog has many problems. Okay. So I was talking about. So this is PMOS or NMOS. Hmm? This is NMOS. And this, of course, has to be PMOS. Right? As I told you, there are four terminals. We draw four terminal also. Wherever you are seeing this pointing arrow, that's the source. Wherever you are seeing the pointing arrow, it's source. Gate is available this side. Opposite of source is drain. And this one is, you can call it body, substrate, bulk, whatever you like. Right? So this is NMOS and PMOS. But the beauty of this particular device is it's symmetric. You cannot say that whether this side is source or this side is drain. It's symmetric from both sides. Right? It's not like BJT. So that's why all the people who are expert, they don't draw like that. They are like drawing like this. So with bubble, it's PMOS. Without bubble, it's NMOS. And there is no pointing arrow. Any one of them is source, any one of them is drain. But note that in the case of PMOS, source will have higher voltage than drain. And in the case of NMOS, source has lower voltage than drain. So using this particular thumb rule, you can find out whether which side is source. So it's exchangeable, by the way. Source and drain can be exchangeable. But this is the thumb rule which works in 99% case, but there are some cases or 1% case is there where these thumb rules won't work. So we'll discuss that. But 99% cases this will work. Okay. So any doubt till now? Or so if there is an NMOS, okay. So why you study transistor, by the way? what is the use of transistor? If you don't study transistor, is there any harm? We have already studied circuits called R, L, C and diode also. Right? We have studied that. So what is the use of transistor? Why we are studying transistor? So active is more dangerous because you need power supply. Right? So RLC diode does not. So like the point here is you cannot amplify. This is what. But you must have studied some. Okay. I'll ask you one question. If this is 1 volt sine wave, what will be the output? So 1 volt is maximum one. This might be minus 1 volt.
So from 0 to 1 volt and constant.
Okay, so you are saying 0 to 1 and constant, right? What about this one? By the way, the name of this circuit is peak detector. And name of this circuit is clamper circuit. Okay. Yeah. So what do you think? What should be the output? You are giving the answer for second one or? 0 to 0.7. Okay. So you are saying that it's because. Okay. So if it is ideal, then 1 volt. Right? Let's assume that this diode is ideal. Yeah, you are right by the way. In the case of the real diode where 0.7 volt of actually drop is there, then it's not going till 1 volt, but it's going till 0.3 volt. Because there are two voltage sources in series. So this is 0.7 and this is minus. So other side you are going to see 0.3 volt. You can try it. Like. It's not easy by the way. If you have not done it, it's not easy. But you can try it. What is going to happen? What do you think? This diode is forward or reverse bias? When you are at the positive half, reverse bias. So there is no use of that, right? It's open circuit. Let's assume that it's to start with, like we are not making the things complicated and we are considering this one as ideal diode where the cut-in voltage is 0, right? So if this is open circuit, what's the output? But this is just still 1 volt. What is going to happen to this diode? If this potential reaches 1 volt, okay, you think about it. The answer is given in the book, by the way. Okay, so there is one diode circuit, like chapter named diode circuit. You can see clamper, clipper circuit, all these different circuits are there. Where I should have 1, 2, 0. So surprisingly, it's going beyond 1 volt. By the way, we will discuss maybe next time. You just go through the book. Okay, I just want to see that you can read the book. And the hint is, if it is plus sign, if you are applying something, minus will be there and same is coming here. So at some point of time, this diode will not remain in the reverse bias, but it will become forward bias. And when it's forward bias, you will have some extra DC potential on top of which you have the output. Actually, it will not like this in reality, something like this. So this is called clamper circuit. It clamps the output at whatever you are applying here. So it will clamp at 1 volt. And if I add both the circuits together, if I add clamper plus pin detector, what I am going to see? If it is ideal, I am going to see 2 volt. So after applying 1 volt sine wave, the output is 2 volt. You can see that. So the claim that the RLC and diode circuit cannot amplify does not hold over here. By the way, what circuit I made? By this one, clamper plus pig detector is known as voltage doubler circuit. So it doubles the voltage in ideal case. So this is not the case. And that circuit is very popular. You are going to revisit that. I'm very sure. Are you taking power electronics course now? So whenever you are going to study power electronics, all the power electronics circuits are using voltage doubler with transformer and other things. They don't use transistors so often. Right? They use RLC and diode. They are happy in RLC diodes because these transistors are weaker ones. By the way, what we are using is 5 volt and minus 5 volt, or 10 volt and minus 10 volt, and whatever you are using in your mobile phone, it's 1 volt. So these transistors are weaker. You need the power MOSFETs for that one, which can sustain 100 volts or 150 volts. But what if I want to use the power electronics industry where the voltage is in megavolts, right? You heard about this, right? Megavolts, kilovolts. We don't use transistors over there. We cannot use. So then you have to follow all these techniques, peak detector and voltage doubler. So you are going to study the circuits which are based on diodes or the RLC. But the only problem here is these circuits are really big or the bulkier one. It can amplify, but it requires lots of area. We don't like all these things. The common man wants to have the mobile phone in the pocket, not like a big laptop, right? So like a mobile phone which can go into your hand only, or camera as small as possible. So for all those technologies where it's smaller technology you want for communication purpose or for RF engineering, micro engineering, antenna, all these people wants the smaller circuits that can be possible with MOSFETs or BJT. So that's why we are studying transistor. But in the case of power electronics, you have to revisit RLC and diode. I suggest if you are having problem in understanding diode circuits, You can follow that, right? I'm going to keep one surprise quiz on that. Okay, so please study that, and I'll keep. So there are very few circuits, right? Rectifier, circuit detector, clipper, clamper, right? So you can use that. Although this circuit is known as it's clipper, or this one is clipper. Such circuits are known as clipper circuits. So majorly the rectifier detector, clamper, clipper, and then just you have to go through that circuit once. Okay. Okay. So this was one of the application of transistor that we want to amplify with the smaller size circuit. But what is another application of this transistor? As I told you, like this technology called CMOS become very popular in the case of digital. So what do you expect the operation of transistor in digital? What do you want from transistor? Do you know this word inverter? You know, right? Some people call it not gate also, right? You know how actually it works, or how it does it look from inside? Okay. Let's assume that there are two kinds of switches. So this switch is the one when I am applying here logic 1, then whatever is available here, it will go this side. But this switch is the one where you apply logic 0 here, whatever is available here, it will go that side. But in other operation, it's open circuit. Right? So these are the switches. There are two switches. So let's assume that I'm making a circuit which looks like this one. So here is input, here is VA, here is VB. So if I apply input as logic 0, what is the output? If input is logic 0, what is the output? What is the output? Huh? VA. Okay. In the case of input equal to 1, the output is VB. Right? If I replace these voltages with power supply positive side and other side minus power supply, which is acting as this is a digital logic 1 and digital logic 0. Right? So if I apply digital logic 0, output is digital logic 1. If I apply the input as digital logic 1, output is 0. So in digital circuits, the most important part is to use transistor uh, as a switch. The usage of transistor in digital circuit is using that as switch, and whatever input we are applying or whatever the output we are seeing, it will be always in large signal. It's not small signal. Right? You agree with this? Either it will be logic 1 or logic 0. So are you following till now? So we are going to study how it becomes generally NMOS and PMOS can be replaced over here. Yes. We are going to discuss more on switches maybe on Friday. Right? But today, is it okay? Right? I follow. So is there any problem in evaluation and all these things? Right? Sanskar, if you want to see your copy, you can come to my office today afternoon. Okay, after 2. Is it okay or you have laboratory? 2 to 5, you have, are you busy? You wrote me mail, right? Sanskar, Kushagra and Sachit. Okay. And other than these three, if you want to see your end semester copy, you can come to my office. Okay, it's in 8N403. Okay, the top floor of the same building where we are sitting.